remember that all radiation measurements and diagnostic imaging fall into two categories. There's radiation in air, which includes exposure and air Kerma, and radiation in tissue, which includes absorbed dose, equivalent dose, and effective dose. Exposure and air Kerma are both very important in the context of occupational safety and patient safety. We'll start by talking about exposure, which is the traditional way of measuring radiation in air. To understand exposure, we have to understand ionization. When the X-ray beam passes through air or any form of matter, it will interact with air molecules and knock electrons out of orbit. This process is called ionization because ions or charged particles like free electrons have been created, and we measure these ionizations as exposure. So this is the key point. Exposure is a measurement that tells us the number of ionizations in air. So why do we care about this? Well, it's really hard to count the number of photons in air, but we can count the number of ionizations in air. And that's why exposure is used to measure the X-ray beam intensity. If we do anything that increases the intensity of the X-ray beam, this is going to create more ionizations in air. Since we can't count these individual photons, we can count the ionizations. And when we do that, we're measuring an increase in the exposure. The number of ionizations is directly proportional to the number of photons in the X-ray beam. So if the intensity increases, the number of ionizations increases, and the measured exposure also increases. So what else should you know about exposure? Well, every measurement needs units. Length is measured in meters, time is measured in seconds, mass could be measured in kilograms, and exposure is measured in coulombs per kilogram. So what does that even mean? A coulomb is actually a measure of charged particles, like the charged particles created through ionization. 1 coulomb is equal to 6.242 times 10 to the 18th ionizations. That's a huge number. Like, the patient would literally die if they were exposed to a beam that was this intense. So in medical imaging, it's much more common to see exposures in the range of like microcoulombs per kilogram, which is about 1,000,000 times less than a full coulomb per kilogram. Here's another way of thinking about exposure and intensity. Imagine this box represents 1 kilogram of air. Exposure is the concentration of ionizations in air. Specifically, it's the number of ionizations in this box, the ionizations per kilogram of air. This particular box is not showing many ionizations, so we could say it's not very concentrated, not very intense. But of course, that's not always the case. If we have more ionizations, that's a higher concentration per kilogram and therefore a significantly higher intensity. The measured exposure is actually affected in predictable ways by our prime exposure factors. We'll start with the MA. If we increase the MA, this is going to increase the number of photons in the X-ray beam. When that happens, it increases the number of ionizations taking place in air, and we'll see this as an increase in the measured exposure. KVP is very similar. When we increase the KVP, this will increase the number of total photons in the X-ray beam. KVP is commonly associated with beam energy and penetrability, but it also has an enormous effect on the quantity of photons in the beam. When no other variables change, increasing the KVP increases the number of photons in the beam. If that happens, it increases the number of ionization events taking place in air, and that will increase the measured exposure. Some exposure factors are different. For example, if we increase the distance between the X-ray source and wherever we're measuring the X-ray beam, that added distance is actually going to decrease the concentration or intensity of photons in the X-ray beam. This is due to the inverse square law. The intensity of the X-ray beam is inversely proportional to the square of the distance from the source. When our X-ray beam intensity decreases, it also decreases the number of ionization events taking place, and that decreases our measured exposure. There's actually another way of measuring the intensity of the X-ray beam, and that is air Kerma. Air Kerma measures the energy of ionizations in air, and this is different than exposure. Exposure measures the number of ionizations, that is, the number of charged particles in air, like free electrons. Air Kerma instead measures the energy of these free electrons. Kerma is sort of a strange word, and that's because it's actually an acronym that stands for kinetic energy released per unit mass. And like exposure, air Kerma tells us how much radiation is in air. For example, if we increase the intensity of the X-ray beam in any way, this increases the number of ionizations and therefore increases the total ionization energy in the X-ray beam. And when that happens, we'll see it as an increase in the measured air Kerma. Kerma is measured in units of gray, which is a special unit that is equal to 1 joule per kilogram. So exposure is measured in coulombs per kilogram, and air Kerma is measured in joules per kilogram, which is given the special name of gray. These units for air Kerma actually make a lot of sense. Remember, Kerma is kinetic energy, that's a joule, released per unit mass, and kilogram is a unit of mass. 1 gray is a very large number, so it's actually a lot more common in medical imaging to see air Kerma values expressed in milligray or even microgray. Just like exposure, air Kerma is affected by our prime exposure factors in very predictable ways. If we increase the MA, this is going to increase the number of photons in the X-ray beam. This will increase the ionization energy in the X-ray beam, and that will increase our air Kerma. KVP is exactly the same. If we increase the KVP, this results in an increase in the number of photons in the beam. Yes, there's also an increase in the energy and penetrability, but there's an increase in the actual number of photons. That results in an increase in the amount of ionization energy in the X-ray beam, and that increases our air Kerma. Once again, the distance is different. If we increase the distance, this actually decreases the concentration of photons in the X-ray beam. That decreases the amount of energy being put into the ions in the X-ray beam, and that decreases our air Kerma. This relationship follows the inverse square law. So how exactly are these measurements used? Exposure and air Kerma are useful anytime we're measuring radiation in air. For example, you could use exposure and air Kerma to test the radiation coming out of the X-ray tube. You could also use exposure and air Kerma to measure the amount of leakage radiation coming out of the X-ray tube. And you could also use exposure and air Kerma to measure scatter radiation. So how are exposure and air Kerma similar? Remember, both measure intensity. Both measure radiation in air, and both can be used to evaluate the tube output as well as leakage radiation and scatter radiation. But how are they different? Exposure measures only the number of ions created in air, but air Kerma measures the energy of those ions. Exposure is measured in units of coulombs per kilogram or microcoulombs per kilogram, but air Kerma is measured in units of gray or milligray or even microgray.